Hey everyone, we're gonna get started. So, first of all, if you don't know, there's food over there, there's drink at the bar, so feel free to get whatever you want. And today, let me introduce to you Cody McCain. He's coming from a company called Tigera, and I believe you're a solutions architect. That's the title. And today he's going to speak to us about application connectivity at scale, and specifically when it comes to technologies like Istio and Project Calico. So without further ado, Cody.
Thank you. How's that? Is that better? Excellent. So as Frank mentioned, I am a solution architect at Tigera. I've been in the New York area for about 3 years now, mostly in upstate New York. I just recently changed my base of location here to the city. So if you detect a Texan accent, you're not imagining things. So I will do my best to be clear, but raise your hand if you don't understand something or don't understand me, more importantly. In preparing a talk like this, so first off, I need to offer an apology. Originally, this talk was going to be delivered by Christopher Lilienstolpe, who is based out of San Francisco, and he had an emergency he had to attend to. And so I am stepping in to his place tonight. So my apologies for me filling in, and his apologies for him not being able to be here. By a show of hands, I'm just curious right now, how many in the audience are using some type of a container orchestrator or doing things with containers? Okay, good, everybody. I have a section here where I'm going to go through some elementary introduction on some things. I always wonder if it's appropriate to add this. You never know coming into a room what the level of experience will be with the topic, but there are some specifics that I want to point out. So I will try to go through that part a little more quickly, since it seems most of the audience has quite a bit of experience in this area. So tonight we're going to really be focusing on not so much how to containerize and how to run, orchestrate containerized workloads, but how the heck do I connect them and how do I do that at scale? As you all are aware, and probably many of you work for organizations that are operating at very, very large scale, all the rules change once you pass certain thresholds. And so I want to introduce to you two different technologies tonight. One has to do with how are we going to connect and issue policy between containers at layer 3 and 4. And the other technology is how we're going to connect services at layers 4/5 all the way up through 7. Now, as you can imagine, I can't get into incredible detail, or we'd be here all night long on both technologies, but I wanted to show you what are some of the directions that are being taken right now in providing that connectivity across all the layers of the OSI model. And to begin that, I first realized that we're all coming from a different perspective, right? So we've got, this is a DevOps meetup, obviously. So we've got some devs, we've got some ops, we've got some people that do both. We've got, in a lot of enterprise organizations, we also have other concerns represented, security concerns, risk and compliance concerns. And so coming up with ways where we can remain agile in that we delegate responsibilities to individual teams to make decisions on how their components or their microservices or their pieces of the software that make up your platform are configured and deployed. How do we balance that agility with also ensuring that some type of global compliance is met? So let's start with some basic examples, right? Everybody knows SOA. SOA is nothing new. If you look at the history, you probably could go back to the 1970s when various modular programming concepts were really beginning to take shape. And so I'm defining it here as some type of a process that needs to communicate with another process. And internally in that process, I can have modules and components, right? But we're moving to a landscape where more and more that component is actually shrinking, and we're having fewer components within that process as we move towards microservices. And specifically, as we do that, we're dealing with processes, what I would call out-of-process communication, right? So I'm not talking about communicating between my components with a library call or a function call. We're talking about network calls. And so networks have become the layer that allows us to agnostically build components and allow them to communicate with each other, right? As long as we speak some type of a wire protocol in the network, I can start plugging my components and be agnostic to language runtime, etc. As I said, we've evolved, right? Anybody in here old enough to have experienced the pains with me and Corba? Yes, all right. So no more orbs, right? We migrated towards ESBs, right? So enterprises loved this because now they could centralize a lot of the control, especially your risk and compliance guys, right? Unfortunately, that always introduced a layer of bureaucracy into the mix. So as we continued along, we got a little smarter in the way that we started delegating control of services, but now we had this idea of API management. So we have these ideas of, being able to discover an API and being able to choose as a individual team or organization or sub-organization, what services you want to consume and what services you want to publish. Still requires an architectural oversight, right, to ensure that a platform has all the necessary components and we've got the right level of granularity as we divide our software up. But again, we're just continuing to build on previous generations and the knowledge and evolve this concept. Microservices aren't anything new. We're just evolving the way that we approach them. And the way that we connect them is nothing new really in terms of the overlying services, but what we're going to find out is the way that that's implemented and the actual data paths and the possibilities of this are going to be, I think, welcome to the whole community. One of the frustrations that I always had with these types of evolutions, right? Who's been part of a project that has said, oh, the new thing has come along, right? We're going from Corba to ESB now. We have to basically rip out everything that works or was working and go to this new technology, and who enjoys lift and shift, right? I think that things are going to be different with this service mesh context, and we'll get into some of the reasons why. So I'm defining that today most of us agree that a microservice is a good approach to modularizing our software. We look at things that are independently deployable, out-of-process components, as I already mentioned. We have a limited domain scope, and as always, we've always had strong contracts, but the neat thing about the way that we do it now is we can independently replace pieces of the platform without having to compile and redeploy the whole thing, right? And you all know this. You all work with microservices on a daily basis. Again, same idea. We're going across the network, but I do want to introduce a term. As I go through the talk, I'm going to talk about a workload. And so what I mean by a workload is one or more microservices that are acting as a specific process. And I'll even get more specific. I'm going to use a lot of examples from Kubernetes. Kubernetes users in here? Anybody? Awesome. Any other orchestrator users? Mesos maybe? Okay, cool. So with Kubernetes, I'm gonna use that as my primary way to show the examples tonight. We have this concept of a workload, right? So these microservices can share a network space, and they operate as a unit when talking on the network. So for example, if I had multiple microservices in this workload and they all wanted to talk on the network, they would have to talk on different ports, right? Because there would be port collisions if they all wanted to be a web service and be on port 80. So a workload basically can be implemented as, if you just want to do a bare bones OS, right? Put your workload on there, put your LAMP stack or some type of Java stack, and start serving up your service. You could also have like a virtual machine with VMware or OpenStack or another VM provider. At that point, the workload then is centralized on the VM boundary. And then finally, most of us have actually started migrating towards containers because they're a lot more efficient, and frankly, they're faster and easier to start up and deal with. So I'm going to use the OSI model. It's not my favorite model because I don't think it fully represents some of the design considerations that you have to think about when you're building your network and deciding which layer to assign communication or a concern to, but I think it's a sufficient layer to talk about the two technologies that we're discussing tonight. So in the OSI model, the way that I tend to look at that is towards the bottom of the model, we typically have more ops concerns, right? And that's at least from a legacy classic view of enterprise IT or just IT in general. More of your ops folks focused on the bottom part and your development folks focused on the top part, right? And so we're going to look at that and how those two things can work together. And by the way, this isn't prescriptive, right? I don't mean that only ops can look at layer 1, 2, and 3 and only devs can look at the higher layers. We're mixing and matching those and taking a much more heterogeneous approach today. But we're going to look at the two technologies. So Calico here focuses on 3 and 4, which is primarily your transport and network layer. So we're dealing with IP and TCP and UDP and those types of things. And then layer 5 through 7, we're dealing more with specific protocols, specific wire protocols. So, think HTTP, for example. So our agenda tonight, I'm going to try to, in both of those technologies, talk about these different areas. So on the bottom, we're going to talk about what an endpoint is within Calico. We're going to talk about how Calico actually separates the concerns of reachability and policy. Too many frameworks have kind of put those things together or centralized them to one device, and we try to separate those apart. And then on the top layers, we're going to discuss what is a service mesh. We may not come to the right conclusion what a service mesh is, and a little bit of a warning about the conversation tonight. It could change. Some of these concepts are evolving every day. We're going to be specifically talking about Istio. It's still in alpha state, so what I say tonight may evolve somewhat. So if you want to be part of that, join into the community. We're always looking for participation. Anyway, we're going to try to talk about what service mesh is, what components make up the Istio control plane and data plane, and if we have time, we may get into a demo. If not, I will post some files up to my GitHub within the next couple of days and walk you through a demo if you'd like to do that. And by the way, there's a great sample app on Istio's and a Project Calico site for standing up demos using all your favorite orchestrators. So if you want to pick that up, I'll put some contact information up at the end, and feel free to ping me up on the community Slack or by email or Twitter or however you want to get a hold of me, and I'll help you through that. So we know, as you guys all know, and by the way, I should have included Squarespace, our host, on here tonight as well. All of these companies are being very successful with a native infrastructure, right? Google, they completely skipped over the concept of a VM. They went straight to containers. Box has adopted Kubernetes at this point, and we're seeing that underlying Bluemix, they're also running their container service with Kubernetes. It just makes things scale more quickly and more easily, because now I'm not having to deal with both managing operating systems, right? I can do things in a much more unified way across my OSs. They don't have to be app specific because of the container abstractions. And I can respond to events and my users' needs more quickly because containers are just a lot faster to initialize and create and spread around and reschedule and all the wonderful things that a dynamic fabric and topology of a platform would allow. So let's dive in first off and start talking about container networking with Project Calico. So, by the way, everybody's probably seen the cute Calico cat. I'll give you a little history on that. Calico uses a cat because it's great to market with cats on the internet, but that's not actually how it started out. So a lot of the founders were either from or working in the UK when Project Calico started, and Calico was actually a type of fabric you could buy that was the simplest type of fabric. I think it was a 2x2 weave. And when we think about networks, a lot of times we refer to the network as a fabric. And so what motivated Project Calico was they were running into all these crazy situations with customers and a Metaswitch with, how do we deal with setting up VLANs and dealing with the security when this app needs to have a pinhole through a firewall to this other app, and we were having all these multiple firewalls in between, and it just seemed like the fabric was way too complicated. Add to that the move to multiple data centers and starting to spread data centers globally and deal more with global traffic. And the existing technologies of the day just were not dealing well with that type of change in requirement. And so they thought about some things and basically decided that layer 2 was not the right answer, right? What is the biggest network that we know? Internet, right? And it scales and handles handles topology changes and scale and can push a lot of traffic, and everything on the internet operates at layer 3 and uses things like BGP to exchange routing information. And so if it can work for the internet, why can't it work for the data center? And by the way, we're seeing more large-scale data centers go to a layer 3 only topology. Simpler, it's easier, and it scales better. We also wanted something that was secure, and of course that basically came back to policies, but we wanted it to be secure in a way that didn't require navigating, if you will, with your compass through the firewall jungle to figure out, the data route or the data path from one service to another when it came down to, troubleshooting and debugging time. And so the idea here was to move policy as close to the workloads as possible and then come up with a better way of matching senders to receivers in the way that we do policy. So we're going to talk a little bit about that. So before we begin, let's talk about what is an endpoint. We define an endpoint in Project Calico basically as a virtual network interface associated with a host or virtualized workload. So let me show you an example. If I have just a physical box, right, so I've got some physical hardware, maybe I got Linux on top of it, and I got a couple apps running. In this situation, those apps are binding to a specific IP and port associated with that interface. We call that interface ETH0 in this case, our endpoint. If we move that to a VM, now we're dealing with a hypervisor in between, so we may have some virtual NICs that are bridging and abstracting underneath what the actual physical layer 2 connection is to our network. But from Project Calico's perspective, we still see, since there's an entire network stack in the virtualized Linux box sitting above the hypervisor, we still see ETH0 as an endpoint. And specifically, you'll see I call it a host endpoint. We actually have two flavors of endpoints. We have host endpoints and we have workload endpoints. And host endpoints typically are associated to workload components of our system that are considered static or that need to be manually defined and advertised to the Calico data store, whereas a workload endpoint is an endpoint that's assigned to a process that was dynamically created or scheduled, right? So we would use something like the metadata from Kubernetes, for example, to know when a workload is, the life cycle of workloads being created or destroyed, and match the workload endpoint at that time. So finally, that brings us to containers. I'm not going to get into the specifics of containers. If you haven't dove into the specifics, I highly recommend you do. The one thing I'll talk about on containers is that a container is just a process, and there's really nothing special about a container other than the kernel namespaces and control groups that are applied to it that allow that process, or that mitigate what that process can see and what that process can use. And so the way that we implement network connectivity in a container is we typically use a virtual Ethernet pair, and we hang one of that virtual Ethernet pair into the container, and we call it ETH0, and we hang the other end into the namespace, the root network namespace in the kernel, and we call that, for example, Cali, some name of an interface. And it's to the, we always deal with interfaces, network interfaces that are actually in the kernel, not in the container. One of the reasons we do this is for security, right? If we have a container that somebody breaks root on within the container, we don't want them manipulating any types of rules that we've put in place in the separate access control lists, that you would set with like IP tables or the forwarding information base, that's within the container. We want to be able to control, all the entry to the network at the host, because usually that's a lot more tightly locked down. So let's talk about reachability and what we mean by reachability. So when a container, or a host, let's start with the host. When a host wants to send something from one host to the next, typically in this situation, they're physically connected via layer 2. They may be doing layer 3, but they're physically connected to a network fabric, and sending from host 1 to host 2, there's no intermediaries involved. There's an ARP request that's done, and basically packets can be sent from one host to the next. Where things get interesting is when we start introducing some type of a orchestrator and some type of a container framework or runtime framework. So in this case, let's say I throw containers A, B, C, and D into the mix. Throw the first 2 containers on host 1, the second 2 on host 2, and I want container A to communicate with container C. Now I've got an intermediate involved, because if you remember from the previous diagram, each of those containers has an Ethernet 0 interface in them, but the other end of it dangles off into the root network namespace of the host. So the host actually has to act as a forwarding agent to move the packets onto the network and across to the other host. So there's a couple things we have to know about here. Well, number one, container A, probably doesn't need to be making decisions on how to get the packet to container C. So that's going to be up to the host 1 and host 2 to figure that out. Another thing that we want to consider is we don't want to have, before Calico came along, there's been some other frameworks, and we don't want to have special cases, right? We don't want it to be a special case if container A is talking to container B because they're on the same host versus container A talking to container C on another host, right? We want everything to be homogeneous in the way that we evaluate both reachability and policy, because we want things to be able to move and shift around in this dynamic framework. So the way that we do this is we introduce a distributed key value database. Familiar with etcd? Similar to something like Zookeeper, and there's a couple others out there, Console, for example, but we use etcd. In our newer versions of Project Calico, we actually also support using custom resource definitions. Previously, we were doing TPRs, but they just changed over to CRDs within Kubernetes, and so we can actually use the Kubernetes schema as a mechanism to store the same data. But basically, we need a distributed key value store. Another side effect of this is that we can scale the number of hosts to the same size that the distributed key value store is going to be handled in terms of, read and write updates, right? So once we start approaching about 5,000 nodes, and that's something, we have to start considering what etcd can do. And as time goes on, these things will improve, but these are drivers when you're thinking about an overall topology of where you start breaking up your clusters and your fault domains and those types of things. We're not going to get into that tonight, but if you want to talk to me about that later, I'd be more than happy to discuss it. So we take that etcd database, and remember I talked about the dynamic workloads, right? We're watching all the metadata that's in the orchestrator. There's lots of different orchestrators out there, so how do we watch all that metadata? Well, we provide a plugin system that helps us do that, and their plugins are very specific. So we have a specific one for OpenStack, a specific one for native Docker, a specific one for Kubernetes, for example. We watch that metadata, we canonicalize the data coming out of those orchestrators, and we send that data into etcd. We also go and put an agent on every single host that's going to act as a forwarder. So ultimately now we're basically taking our Linux hosts, which by the way have an incredible stack that handles routing. It's very mature, and we're turning each one of our nodes into a router instead of having to send it upstream somewhere else to get routed. And so by turning every single node into a router and putting an agent on every single node, we've now distributed our control plane. So there's no God box here. There's no central point of failure because both our database is distributed and all of our agents are distributed. And as changes occur, we are eventually consistent. But as changes occur, then they basically get distributed, throughout the entire network fabric. So what does Felix do? Felix watches for changes. And by the way, one neat thing about etcd is, and the way that we watch for changes, we only watch for changes that are applicable to the host that Felix is running on. So we have very tightly scoped event loops. And Felix only wakes up when he needs to make a change. The other thing Felix does is runs in user space, right? So Felix is never in the data plane, in the data path. Everything that we're talking about tonight stays in the kernel from end to end until it gets delivered into the container and processed by the application. So application A or container A sends a message to container D. Everything is going to go through the kernel end to end. The only thing that's happening in user space are updates to either the forwarding information base, the FIB, in the root namespace of the host, or the access control list. So Felix is responsible for maintaining both the ACLs and in some cases the FIB so that it can provide a pathway for the containers not only to receive data but to also talk to the world, right? Because they may need to go out, maybe not to something internally within the network. They may need to go out to Google or some external service to talk with the world. So far we've got a way to program routes. Now, how do we share routes? So before I get into that, in Kubernetes and some other, and it's also a standard that's being adopted by other orchestrators, there's this concept of a container network interface. It's CNI. And it is an abstract way for various network fabric providers. So think GCE, for example, or think eventually, I think Azure has one that's fairly mature now, and there's some others out there as well. We actually implement CNI if you're not using an existing cloud provider that provides it. But what CNI does is it allows you to call into the interface, and when you create a container, it takes care of setting that container's network access up. So everything we've talked about up to this point, we've talked about it from a point where we're doing it, but there are some other ways where you can use a pre-built or built-in capability of a cloud that can do all this for you. And it does things like IPAM, manages your IP addresses, et cetera, that are assigned to those containers. But in the cases like a on-premises installation or some other physical installation where that's not available, we take care of that for you. So we also want to be very cognizant, as I talked about some of the scalability concerns, right? We may want to, for example, in a very large-scale data center on-premises installation, we may have multiple racks that make up clusters, and those clusters may be tiered together in some type of a class network design where each rack or cluster becomes a fault domain, those types of things. And we need to move data between those clusters or those racks. And so we are relying on the network fabric to help communicate routes to either the individual containers or some other endpoint within our rack. And since I said that most of these data centers are going to layer 3, typically BGP is used to communicate that data. So we want to be compatible with BGP. That is, we want to be able to take our container network and be able to exchange routes with the network fabric underneath the container framework, or underneath the hosts that are hosting underneath the hosts that are hosting our container orchestrators. So we run Bird. Bird is an open source, very well proven BGP client that can either, we can operate in one of two ways. We can either form a full host-to-host mesh, so every host knows about every other host. And how do we do that? Well, one of the things is we have an etcd distributed database, so we know all the hosts that are participating. Or we can, in larger installations, when you start looking at the number of interconnections of a full mesh, by the way, they operate at really large scale, right? So before you have to move away from it, I would say most people are not operating at that scale. But you can move to something like a route reflector, and so you have an intermediate BGP talker that's advertising your routes at a central point. So for example, in a physical data center, that might be at the top of rack switch or router. And we can peer with those route reflectors. Both of these agents are sitting there making changes to the networking stack in the kernel. Bird, what it does is it primarily listens for other routes. So for example, container A, Felix over here on host 1 knows that container A is there. It wrote a route from the host to container A. Bird is watching that route table and says, I see a new route. So I'm going to advertise to all my peers this new route, and it does so. Bird sees that advertisement, and Bird writes the route to the kernel so that when container C wants to talk to container A, it knows what the route is. And that's how the data is able to be sent across the network fabric to container A. So again, underneath the hood, if we actually look at what principal objects are being changed in the kernel, we are basically updating the forwarding information base and the access control lists. And we'll get into policy here in just a second. We have our own Cuddle tool. I'll say kubectl, kubectl. I like Cuddle. We just released some pretty cool stickers that have like the Calico cat. It says Calico Cuddle. But anyway. So we have our own Cuddle tool, Calico Cuddle, that is able to update the etcd API. One nice thing about Calico is it has native support for Kubernetes network policy. Part of the reason is that we wrote it. So it looks very similar to the Calico policy specifications. And so the database or the internal data structure, data store for Calico can either be updated via Calico Cuddle, or in some cases, we've got the plugins atop that are watching metadata, everything from what containers and pods have been created to, in some cases, we're looking at other things such as network policy and updating the data store as well. So we have a compatibility layer so that if you're more comfortable using something like Kubernetes network policy, you can do that instead. There are some features, though, that aren't supported that you have to move to the native Calico solutions to get. So let's talk a little bit about this policy model. So we have workloads that want to basically send, traffic from one endpoint to another. So what we do is we basically have two concepts of ways that we set up policy. Profiles tend to be something more static, right? So they're assigned at build time or at provisioning time, and we assign those to more of these static host endpoints. And these are, it may be something like, for example, we only allow you to talk to an internal DNS server. We're not going to let you reach out to 8.8.8.8. And these profiles get evaluated at the host endpoint or static points. We also have the concept, though, of a policy that applies more to our dynamic workloads. And by the way, policies can also apply to the static workloads because what we support is the concept of labeling. Everything uses labeling when we're talking about these dynamic structures. And so what we wanted to do is provide compatibility because we're already labeling things in your orchestrator, right? We're labeling them in Kubernetes, et cetera. So we want to provide support for matching or using those labels as a selector and a criteria when we are deciding which policies are going to match. And so we have this concept of labels and selectors. It's the exact same way that it works in Kubernetes when, for example, I create a service and I want to match it to a set of pods. If I create a policy and I want to match it to a set of labels, we have an evaluation syntax that allows us, or DSL that allows us to do that. We also have some other operators and interpolation functions within that DSL, allow you to do other things like ask if it's a host endpoint or workload endpoint, some of those types of things. So for example, if I wanted to write a Calico policy, it might look something like this. The first thing is that I give it a name, allow TCP 6379. But the most important thing is the first line of the spec. And by the way, all this ingress and everything here is also, this is all YAML, so it's all indented underneath the spec. The selector tells us what labels, and again, these are Calico labels, but in the cases where orchestrators have a similar layer, they will get converted over to Calico labels as well. But this is telling us the criteria by which to match this policy to workloads. So this is saying match this policy to all workloads that have the label role with the value database. In this policy, I specified two separate things. I specified an ingress. So I'm going to allow any inbound traffic on using TCP from another endpoint in the system that has the role front end. I'm also going to only allow TCP traffic on port 6379. A nice thing about policies, you can have multiple policies. Policies are evaluated in order. So you can specify the order of the policy and the actions that you want those policies to take. So we've got various actions like pass or deny. In some cases, you may want to log or allow. So the ingress is specified there, and then of course on the egress, we're just basically saying let this particular workload, whether it be a VM or a container or a specific host, talk to anybody that it wants to. Question? So the question was, can we make the policies immutable? The policies by definition are immutable in that the policy gets rendered on whatever the available set of containers or workloads that are in the system at any given time. So the policy doesn't change. If the workloads underneath change or change their labels, for example, then different policies might be rendered. And by the way, we do that in real time. So Felix and the etcd watch is sitting there watching these policies, and if it sees a label change or something where it needs to make an update to its local IP tables rules back into the ACLs of its kernel, it immediately makes that change. So as soon as it's just like anything else in a declarative system like this, as soon as the declaration is made, the controllers in the system, in our case Felix, are acting to realize the state that's been asked for and it's been declared. And we find that in really large systems with lots and lots of policies and rules, I can't remember the exact number, but it's on the orders of thousands or millions of, I think it's on the order of millions of policies just in a test setup. We can get convergence times in under 10 milliseconds, on 1,000, 1,500 node, 2,000 node clusters. And the reason we can do that is, number one, Felix is only, listening for things that apply to it. The other thing a lot of people ask is, okay, that's great. So what if I have a lot of policies, right? So how is that going to affect, right? If I'm adding a lot of IP table rules, how is that going to affect my performance in the kernel? Because now I'm having to evaluate all these ACLs for every time I forward traffic. And the way we handle that is everything is actually big O of 1 in terms of the evaluation, because we use IP sets and the way that we render the policies and the the effective output of that policy. Other questions on that? All right, so we've pretty much covered both reachability and how we're going to protect these workloads at layer 3 and 4, or at least an introduction to that. There are other things to consider. How do we secure host endpoints? Shameless plug, I've got a blog series going right now on that if you want to check that out on Tigera's blog site. But there's a lot of other things that we might want to consider in terms of large data center design and topology. We may want to think about how we move traffic between the container network layer and the underlying physical fabric. So those are all more advanced topics, but we pretty much summarized how we're going to get packets from one container or workload to another. So let's move up the stack now and start talking about layers 5 through 7. So going back to the evolution that we've seen in the way that we move packets between workloads, right? This idea of SOA, service-oriented architecture. We are now in this idea of the microservice. And for the purposes of this discussion right now, we're primarily talking about HTTP. But let me make a caveat here. One of the things that's really frustrated me about some of the other things is when the underlying wire protocol or interface mechanism or interface contract changed due to a technology change, right? The previous mechanisms of connecting those workloads required a redeployment or recompilation, or we had to change the way that we actually built that interface. What we're trying to do here is elevate the way that we connect services, it's layers 3 through 5, up into its own layer that's really opaque to the underlying workloads. They really shouldn't care how data gets from point A to point B, and they really shouldn't care what other instrumentation is being attached to that layer. That opaque layer should be flexible enough, though, that it can be plugged so that it can handle different types of wire protocols for moving that data. So right now, HTTP is very popular because of REST, and we're seeing a lot more movement to things like gRPC and other binary protocols because they're very efficient. And of course, HTTP 2.0 is out and adds additional features to that mix to make it even more efficient in terms of multiplexing connections and other goodies. But we know that layer is going to continue to evolve. So we want to basically lift it up away from the containers. The other reason that we want to lift it into its own layer is how many work in organizations that use more than one runtime framework in their production systems? Yeah, of course, right? We'd be fools if we didn't, right? We finally figured out that everything's not a nail, and then you can't use a hammer. Pick your favorite analogy, right, or your favorite saying on that. We want to choose the right tool for the right job. And so whether you decide that JavaScript is your tool in Node, or you want to use Java or Go, you pick the runtime framework, but it shouldn't be something that is specific to the transport that's happening between those services. And so we want this to be really polyglot. An early iteration of this, if people in here are familiar with the Netflix architecture. So the Netflix architecture was really popular, right? And it was a great architecture. This isn't a ding on them, but it was fairly Java heavy. And there's been some adaptations that have been made to it over the years because Netflix was very Java heavy in the way that they implemented a lot of back-end services. But that basically targeted a specific framework, and we're trying to avoid some of those lock-ins and elevate that out so that now we can have an agnostic and hopefully polyglot interface for connecting these workloads. Do a little bit of review here. This is for those who maybe are a little new to Kubernetes, or for those that want to kind of understand what's going on. Because I may mention some of these terms as I'm talking about Istio, and I'll go through this pretty quickly. So in Kubernetes, we have masters and workers. Masters are coordinating everything. It's a server where all the control plane is running for the most part. There are control plane elements, such as the kubelet and kubeproxy, that are living on the workers. But workers is typically where you put your workloads. In each of those, if you look over at the master side, there's various work or control plane components that I've listed, such as the API server and the schedulers and the controller managers. One thing I wanted to point out is this whole idea of the admission controller, because that's going to become very important soon in Istio in the next release. What the admission controller does is, since Kubernetes is so API driven, meaning that there's no back channels between any of the components that are coordinating with each other, everything goes through the API server. So all the watching and all the declaration changes of state, they all go through the API server. And the admission controller is this cool component that is basically able to change the world on any API as a request is coming through, right? So it can overlay some type of a transform based on metadata about the environmental configuration of a cluster, or maybe session data, what user is calling an API, et cetera, and it can transform that call to either inject additional information or state in the declared state change, or maybe deny the call, et cetera. And that's going to be really important to Istio, so keep that in the back of your mind. I also already mentioned the CRD and what was called TPRs before. CRDs are custom resource definitions, and this is Kubernetes' way of allowing, since we already have a great way of using the API server to centralize all the changes, we can use CRDs then as another mechanism to store custom objects related maybe to some Kubernetes operator or function that we have deployed on Kubernetes. Over on the worker, we have pods. I've already kind of talked a little bit about what a pod is, but that's our form of a workload. And in Kubernetes land, that can be one or more containers, but everything in a pod is sharing the same network namespace. And so we refer back to the definition I gave of a workload earlier. And then finally, we've got, I already mentioned CNI. We've got kubeproxy and kubelet. So kubelet is just the agent that's interacting with the local container runtime engine, making sure that things that are getting scheduled to a host actually get spun up in the container runtime. And kubeproxy is implementing the abstraction for service VIPs. So Kubernetes has the concept when you create a service, it can associate a virtual IP to that service. And so the virtual IP really doesn't exist other than a series of rules that are written into the forwarding information base via IP tables by kubeproxy. And so it'll see a VIP and it gets translated and essentially masqueraded on the fly on every host. What we're about to talk about with Istio is it actually, in some cases, replaces the need for kubeproxy in terms of service-to-service communication and also discovery. The other thing services and kubeproxy can do is they can integrate, or kubedns can integrate with the metadata and provide naming support in the cluster as well. Something you might get in older systems or other systems with, something like Zookeeper or Consul, would provide their own DNS services. Kubernetes also has a solution for that. Each one of those workers has additional things like storage and certificates. We already talked about them acting as routers, and they may have other types of things like SE Linux and other ways to secure that host. So in Kubernetes land, these are the main concepts, right? So this is just an overview. We've pretty much gone over just about everything except ingress and kubedns at this point, but this is how Kubernetes talks about connecting services and workloads to each other. So in terms of ingress specifically, there are basically two ways to do load balancing. You can do network load balancing, which is similar to like if I went into Amazon and I spun up a network load balancer, and I did, basically I'm forwarding, at the TCP layer, or I'm doing packet forwarding of some sort. Or you can do application load balancing where I'm running a proxy. So I'm basically accepting the connection and the request, and then I'm making another outbound request on the other end, something like what Nginx or HA proxy. Pick your favorite proxy. In our case, we're going to use Envoy that can do application load balancing. And so ingress is a way in Kubernetes to specify how that application proxying should work in a proxy agnostic way. So I could use Nginx or HA proxy, or in our case Envoy, as the mechanism to actually implement the application proxy. So what is Istio? What is it giving me at layers 5 through 7? The three main things are basically traffic management, observability, some people may call instrumentation, but it's a little bit more than just instrumentation, and security. So let's look and see in each one of these things. As far as traffic management goes, this is dealing with things like canary deploys, blue-green deploys. These are all common scenarios now in very large-scale platforms that need to be able to evolve and iterate components of their platform without having to make a massive, Flag Day approach. And this basically gives us those capabilities. It also does load balancing, and when I talk about load balancing, it does a lot of different types of algorithms in terms of load balance. Round robin, you can basically plug whatever algorithm you want. It can also look at header information on the request and load balance on that as well. So it's great for things like data sovereignty, for example, or other situations you can imagine, and multi-tenant as well. It can also implement quite a bit of fault handling, things like retries and circuit breaking, timeouts. If you write some interesting ways to analyze data that's coming in, it can do outlier detection and things like that. But the neat thing about all of these various things that it's doing is it's also making very heavy use of, rate limiting is a big one, it's making heavy use of hash tables. And so just like everything else in our system, a lot of the decision making can be distributed, and if a calculation was done to make a measurement or to make a decision, a policy decision on those layers, if it's already been made before from various parameters or aspects of the inbound request, that can be actually hashed on the local ingress node handling the request and replayed. And so again, another way that this is becoming very efficient to distribute that. From the observability side, Istio provides tracing, custom telemetry, metering, and logging. And by the way, anybody here operating large container systems without tracing or tried to debug a system without tracing? It's crazy, right? So with scaling and all the other, the dynamic loads moving around, and we certainly don't want our developers execing into a container, dumping logs. Tracing gives us the way to basically track a call from endpoint, from end to end, and be able to look at various instrumentation pieces, what's causing various lags in that call, and also where I may be experiencing errors or something. And then finally, it provides security as well. So one of the important things is it does identity, where we have teams that are constantly deploying new containers or possibly new types of services. Having a centralized way to maintain identity, for example, trying to distribute certificates to all of those teams for deployment onto into their containers so that it can identify itself, that really becomes cumbersome. In the case of Kubernetes, it already provides a way to do that for us via the service account. And so what a lot of customers ask for is, can you give me a way to automatically establish a service-to-service TLS connection? Well, to do TLS, I have to trust that the other end is who they are, who they are by asking for an exchange of certificates so that we can build a session. And again, since containers are ephemeral in nature, they're coming and going, and maintaining that static list of certificates is really impractical. What we want to do is we want to have a way to leverage the service account identity that's provided to containers and basically establish MTLS using something like Spiffy, and there's a couple other proposals that are in play right now as well for connecting those two containers. And then finally, we can also implement policy at these layers as well, but we get a different type of policy, right? Policy is going to be specific to the underlying layer 7 protocol that's being used to exchange information, right? So in this case, I might have some policy that if I see a specific HTTP request header, maybe I limit the HTTP verbs that can be used in that request. And I can implement these rules in a layer separate and apart from the actual microservices that are providing that. So if your company has some specific standard or template for how it implements REST, for example, this might be a great way to apply policy globally in terms of who has write and read privileges, those types of things. So a quick look at the control plane. I want to do a quick time check. I know we're getting close, so we're probably not going to get to the demo, but I'm going to run through a couple slides here to show you the control plane, and then I'll make myself available to whoever wants to stay after, and we can talk about some of these more in depth. But I want to honor your time and not go for 2 or 3 hours on this. The control plane in Istio is basically made up of 4 main components. And if you count the Istio Cuddle command line utility, which is part of the pilot project, there's actually 5. So pilot is the way that we configure things in Istio, and it's the way that we deliver our configuration to all the components. Mixer is the way that we process requests. So if there's things that I want to do, like make policy decisions, or I want to record information about a request for later consumption, such as logging or tracing, or if I want to do some other value that's going to be used to determine like routing, etc. All of this is handled by the mixer. The mixer is very pluggable, and it has a mechanism to share data very easily between those plugins so that components can collaborate or be chained together to make decisions about routing, policy, recording of information, etc. And then finally, we have auth, and that's what connects the underlying orchestrator with, like for example, the service identity and helps create the certificates necessary for MTLS. And in future versions, we'll also handle things like establishing user identity principles, some type of maybe OAuth 2 authentication or something on the inbound request, and being able to distribute that all along the data plane. Go ahead.
Question, the ambassador, the API gateway.
Okay.
Do you guys have any plans on incorporating the API, an API gateway of some kind, given obviously how structured APIs are?
I'm not sure I quite understand your question. So are you asking if, so there already is APIs available for Istio and Calico both, in terms of actually specifying like an ingress API gateway? Is that what you mean?
I understand that as an ingress, but
right.
If you're doing a mass deployment,
Sure.
Having a robust API.
Oh, absolutely. These are all API driven. These are all, so take for example even the Envoy component. Everything that in the Envoy component in terms of its configuration is entirely API driven. If I'm going to get down to another slide, I'll actually show you some of the various APIs that are there. And Istio Cuddle is really just calling back into an API, so you can write your own API. It's actually built on top of another library. You can incorporate into your own orchestrators or your own abstraction layer, wherever you want to call it from, and manipulate the control plane. So everything is API driven that we're talking about.
And you'll have a centralized API so that you can manage from there, or you have to call out the API and orchestrate?
There will be some loose coupling, but everything in terms of, like, for example, the Istio control plane, everything goes through for the most part, a centralized API. The Calico and the Istio are different APIs. Shameless plug here, Tigera is a company. We're working on some additional solutions that tie those things together. Talk to me afterwards if you want to get more into that, because there's some really cool things you can do in terms of influencing one set of layers influencing the other. But yeah, everything is API driven. So I mentioned that Pilot sends configuration, auth handles certs, and Mixer handles all the computation. And then down below, since Envoy is sitting inside of the pod, remember we talked about network namespaces, and we kind of got into the weeds of how containers implement their network interfaces. Inside that network namespace is actually the same primitives that you would find in the root namespace, like access control lists, forwarding information bases, things that IP tables can manipulate, for example. And Envoy, when it starts up, for example, in Kubernetes, it actually manipulates that table in such a way that any other containers that spin up in that workload, so for example in a pod, are restricted to sending data. Only basically any data that they send anywhere gets redirected to go through the Envoy proxy. That way the container really doesn't realize that a change has been made, and it doesn't realize it's sending through a proxy, which is great because now our developers don't have to worry about the communications concern between services, right? They can focus on the logic and the API, the service that they're writing. Did you have a question back here? Okay. And then moving along, the Envoy, the other reason we also talked about advantage of Calico from a security perspective is, imagine if I set this up and I'm implementing all my policy at layers 5 through 7. Well, what happens when somebody roots my container and now they start manipulating the things that Envoy already set in my container's namespace in terms of its ACLs and forwarding information base? That's why we have a stopgap down at layers 3 and 4 with Calico. So we encourage from a security standpoint to do security in depth, right, and be able to implement security across all the layers. So why did they choose Envoy? We could have chosen Nginx and HA Proxy, et cetera. And by the way, all those are available, right? Those are becoming available. Istio is not specific to any particular proxy, any particular mix-in plugin, any particular authentication or authorization system. Just like Kubernetes is a specification for how orchestration should occur, and it's up to individual plugins to implement that specification, Istio is taking the same approach. But they chose Envoy as the initial reference implementation for a couple of reasons. Primarily, it's been in production use for a couple of years at Lyft. It's very robust, very lightweight. It's got a runtime anywhere between 7 to like 11 megabytes. And so that allows Envoy to be installed as a sidecar in every single workload that's deployed, which simplifies a lot of things. Unfortunately, when you deploy things in a different way, maybe like one per host or something like that, what ends up happening is you have to have some hacky rules that sidestep some of your policy layers so that you are making sure traffic is going through the application proxy. So by moving it up into the workload, and installing it as a sidecar really simplifies the data path, and it makes everything a lot more secure in my opinion. So those are some of the reasons that Envoy was selected. I had mentioned that everything is API driven. So this is just an example with Envoy, right? There's a cluster discovery service. So all of these things can be plugged, right? So we're plugging them with Istio primitives. But if you wanted to take Envoy and run it outside of Istio, you certainly could. And you could plug in an adapter that maybe use console underneath the hood or etcd or something like that. Because all of these APIs are pluggable even down to the proxy layer. So if we look at a request, basically a request, before a request comes in, things get set up, right? The pilot sends all the configuration to all the different participants. In this case, I've got both an ingress and an egress proxy. I do want to point out one thing with this egress proxy. It's a cool thing for a lot of enterprises, right? Because nobody's going to do a massive 100% migration to an orchestrator, right? You still got legacy systems running. You got databases running. You've got, older Java application servers running. The infrastructure is always going to be heterogeneous. And so that same is true in terms of network policy and the firewalls that you've got set up. So some of the things that you can do, for example, is say that all egress coming out of your cluster is going to come from one or a set of boxes, which simplifies firewall rules, right? So you can do more detailed, finer grained policy rules within your cluster, and even from the services that are allowed to contact the egress proxy, and then between the egress proxy and your upstream firewall, you can add, downstream firewall, you can add some additional restrictions, but say that I'm only going to accept traffic from this egress proxy, which basically ensures that any traffic egressing from your cluster has been evaluated by something like Istio and proxied outbound. On the ingress side, we've already talked a little bit about application proxies, and Istio as well can use Envoy, just like Nginx or HAProxy or another Kubernetes type solution for ingress. It's one of the plugins available. And so I would specify ingress using the standard Kubernetes ingress resource. So we mentioned how, meant to show this, Istio Cuddle talks to pilot and programs configuration, but it could be an API call via a library, etc. Mixer's pluggable backend, and of course, auth is setting up all of the service-to-service security for you. So, where are we at currently with Istio? Guys, this is a very young, gals, this is a very, very young project, so please get involved. The community is very welcoming. They're very willing to get you plugged in, get you working on a pull request. We got a lot of features that still need to be built. Some of the things that we're focusing on is maybe a hybrid Istio model. For example, maybe I'm running Istio on all the endpoints in my legacy system as well as on my clusters, right? And so now I've got a unified service mesh between legacy and some of my newer maybe cloud native development that's happening. Making sure that we can get auth-nz working in a way, right? How many times have you written a solution for auth-nz? I don't want to write another solution, right? It gets old. So we want that layer to handle that for us. Obviously, there's focus on performance and scale, session stuff, caching, a lot of the same things that you would see maybe from the previous generations of SOA. Same topics are up here, right? We're doing a lot of the same things, but we're doing it in a very different way that's hopefully more pluggable, more distributed, and is going to match the topologies of the applications that we're developing today. So with that, I'll offer my shameless plug at the end. We are offering classes on all the above, and training. So if you want to check that out, or if you want to get involved, those are the project websites, our contact website. You can reach me on Twitter at McCodeman, and I will be posting a version of these slides as well as hopefully some code samples in the near future, probably the next couple of days, if I can get out of some duties at home and get those up on the web for you. And then otherwise, feel free to reach out to me. I'm actually new to New York City in this area. I've actually only been on site now for a couple of days and looking for some office space right now. So I will be local here all the time. So if you want to pull me over to your business and chat about things, reach out to me. Give me a holler. Questions? Yes, sir.
So can you clarify a little bit about the responsibilities of Felix and Bird?
Sure I can.
Calico?
Sure.
So as I understand it, I mean, Felix handles things like...
Sure.
Felix handles things like updating, service routes within the kernel itself, and then Bird is responsible for distributing between them.
Right.
In terms of the routes that, for example, Felix is updating on the host, is it getting that through etcd? And basically just sort of what role is etcd playing with Felix? That would be another...
Sure. So Felix is getting all of its data from etcd. So Felix doesn't interact directly with Bird at all.
Right.
We also distribute Bird configuration via etcd. We use confd to do that. In terms of like programming routes, theoretically, we could actually build the entire system without Bird, but then it would limit some of the... We would be reinventing the wheel in a couple of things that BGP already does really good in terms of integrating with the underlying network fabric and
external connectivity,
summary
things like
routes
that.
and making it very efficient. But effectively, you could just say, well, maybe I'm just going to make Felix be able to do all the programming of routes because it already has the distributed database in etcd. All the information is there, right? It knows everything it needs to be able to distribute those things. But the way that it works is that Felix writes into the kernel, and then anything that it writes in terms of, and it only deals with routes local to its host. Bird then is just watching that, right? So Bird has a directive in there that can watch both the direct routes and the other routes, and then it picks those up and advertises them to other Bird clients, which then write into their kernel. So if a container comes up on host 2, the way that host 1 knows about that is not through Felix, it's through Bird, because Bird will actually makes that right.
Right, I understand.
Okay.
I think my question was more about how is Felix learning about the route it needs to add because that container comes up? What's updating etcd to so that Felix knows to look?
Those are the orchestrator plugins.
Okay.
So for dynamic workloads, we're watching the life cycle in the orchestrator and reading that metadata, so we know where the container got spun up, what its IP address is, whether we provided the IP address or another CNI plugin provided that IP address, so that we can figure out what that route is.
Perfect. Just wanted to clarify.
Exactly. Yeah, we watch that. Now, there are cases where we have to manually add those in there because some of the host endpoints are static, right? So there's no way that Felix or Bird can know about that unless we use Calico Cuddle to program that information, or use the API to do that as well. Some people would do that, like, for example, they have a Terraform script that provisions, right? So during some type or Ansible, so they would basically program all those things during the run of the Terraform or Ansible script. Other questions? Go ahead. Sure. We're waiting on a microphone.
Sorry, one other question. So you were saying that Envoy is going to handle all of the outbound connections as well. Is that correct? It's basically intercepting outbound connections
it can.
from...
Now, there's some interesting debate going on. If you want to really get into the specifics, you can catch up on a couple of the SIG meetings that are going on. But it can intercept, by default, it would intercept all outbound communication from a workload and then basically handle carrying it to the next Envoy proxy or egress server, egress service, and out to the external world. But there are some configuration directives to Envoy that can install it as install a bypass, and it can do it. It can match it on basically what is the destination IP, and there's some other configuration parameters, because in some cases you may have existing libraries that are making an outbound call to some TLS-enabled service that has an embedded certificate in it. And so since Envoy is playing man in the middle, it's not going to be part of that certificate trust chain, and you've got to bypass it. There's a whole discussion going on how to handle that situation, actually, and there was an update a couple weeks ago. And I'm not sure exactly where we've landed on a decision yet, but that's a really complicated problem, right? Because we don't want to break this.
Well,
we don't want to break the chain.
If you do that, you know, if you bypass it, you're sort of breaking the ability to do retries and things, right?
You are, but you would do it on a selective basis, right?
Understood.
So it's very valuable. So the service mesh is very valuable for your internal platform and the service-to-service communication. The times that you do have to reach out externally, there may be cases where you have to bypass it because the tool that you're using either has the certificate embedded in it for the trust of the TLS connection, and you can't install a certificate. So I think a lot of even some tools may have to change. Maybe I'm using the AWS, CLI tool, reaching out to AWS, right, as an example. Those things may have to become a little more pluggable or discoverable in terms of the certificates that are used, so that we can either insert man in the middle or come up with some other solution. Good question. We have a question over here.
Thank you. I have two questions for Calico. So first one is, if I use the CRD as the backend, is it possible to specify a separate etcd cluster for Calico? And second, what's the situation with the host port support for Kubernetes? And I have actually one more comment with how the versions are, how the release are versioned. So right now, if you like, the current version is 2.5, and it bundles like 1.9 of this and 1.10 of that. Is it in your roadmap to align those versions? Thank you.
Good question. I'm going to talk about the version one first, because I'm going to tell you straight up, I don't know the answer to that, so I will have to find out. In regards to the CRD, so we've actually supported Kubernetes as a data store for quite some time. Right now, we're getting ready to drop a CRD support. There are still a couple of features that are not in parity with the etcd solution, and so if you want the full feature, I recommend the etcd solution, because it doesn't have all of the parts of the schema yet in a CRD form. And in terms of multi-cluster, that's an advanced question. We definitely can move data across different clusters. We can support, in some cases, multiple clusters. We have to ask what you mean by multiple clusters, right? Are we talking different orchestrators, same orchestrator, multiple instances, VMs to orchestrators? We do support those types of situations, but we have to be very careful with some of the tags. Our highest hierarchy in some of the labeling, which we're working, and we should be addressing. I'll have to talk with our product managers on that. But if you've got collisions with things like namespaces, like the same namespace in two different clusters, some of the policies may match inadvertently, and so I need to check to see how orthogonal some of that labeling is. A dedicated cluster for Calico? Oh, I'm sorry. I misunderstood your question. I thought you were talking about connecting two clusters. So, yes, when we talk about etcd, for a while we were actually on a different version of etcd than Kubernetes. But in addition to that, we definitely recommend separate versions of etcd. We could run in the same one, but it's always better to separate that concern, because etcd is already fairly lightweight. Most of the time, we would run two etcd processes on the same servers that are representing an etcd cluster. We just run basically two separate etcd processes, and that basically gives us a separation of concerns in that security domain. Go ahead.
I've kind of struggled with the data tier capacity modeling. I mean, the size of the architecture. A lot of of us in the enterprise space are coming out of large VM stacks,
Sure.
where, for better or for worse, we maybe over-modeled them. We created too much capacity. But in the container side, the non-data tiers have worked out, I think, or are working out pretty well, because that side was grossly oversized
Sure.
by a zillion X. But the data tier side has been a struggle, and there doesn't seem to be a lot of guidance.
Okay.
There's not, the traditional world of benchmarking and kind of sizing,
Sure.
capacity models.
Because we're
et
moving
cetera.
things around, right? We're rebinning the system on a fairly constant basis. And some of the things that we have to look at, I worked with one organization, we can talk a little bit after this, that's actually using some Monte Carlo techniques in various ways to model both the CPU and memory usage as applications are moving across the cluster. So there's probably some techniques that we can look at for doing that. That's something that our company doesn't, specifically specialize and offer services in at this point, but it's definitely something I'm willing to chat with you about and explore some solutions. But yeah, you're right. Since we're constantly rebinning and we have a dynamic nature of where a workload is going to get scheduled, we do have to have some extra capacity. And I think a lot of times we're pinning the capacity too closely to what we think the maximum number of workloads going to be running on that system, and that's not a good way to approach the problem. Because what we end up doing at that point then is, I'll say this, our ultimate goal is to turn that cluster or treat our data center as the same way we would treat a computer, right? The whole data center is our computer, and we're just spinning up processes. If we make our capacities too small, then we start putting too many rules in on how we segment out which processes can go to which machinery, right? And then now our fault domains become more complicated. Our matching our hardware to the workloads becomes more complicated. All that stuff. So, I think we want to.
You guys are out of the proof phase. This is proven. Now it's the
Yeah.
maturity phase.
Right.
Which is, how do we match?
Oh, Calico, yeah, and Calico specifically, depending on which market study you want to look at, but in terms of Kubernetes workloads, for sure, we probably have 75 to 80% of the market. Google, I'll name drop, they're using Calico for all the network traffic underneath GKE, right? So IBM Bluemix is using Calico underneath all of their service container solution. And there's several other, GitHub is using it under all of its containers. So yeah, we're proven at scale, no doubt. And we can help you with the sizing and stuff, especially as it pertains to the layer 3 and 4. Other questions?
How tied are you to SRE?
To etcd. That's a good question for our product management team. I'll forward it along. I don't know. At this point, we are moving quickly to supporting CRDs and Kubernetes, which underneath the hood is etcd, right? But I don't know why that couldn't be pluggable in the future, because it is a key value store. We just want to find something that allows it to converge fast enough, right? We're getting really good performance in our conversion rates right now when we make a policy change across all the nodes, and we want to maintain that performance. So as long as other solutions are come along that provide us that, the other thing that we are providing is a not at this time, but the only ones we officially support are etcd and Kubernetes. Another thing that we are doing, though, is we're adding an additional component. I believe it's named Typha. That is a go-between between the Felix agents and the underlying data store, so that we can reduce the number of reads against the etcd cluster and can cache in a local way information that the Felix agents need. So maybe we do a Typha agent, per rack, or some other arrangement. And by us abstracting that again into its own layer, if we want to adopt other data stores, we have a really good mechanism to plug that in, right? Because that concern has been well separated in our architecture. Other questions? Well, I sincerely appreciate your time, and I sincerely appreciate the flexibility of our host allowing me to step in at the last minute. Hope that you found this useful, and again, if I can help you in any way, please feel free to reach out to me.
And feel free to stick around if you have any other questions. Thank you.